Welcome to video lecture E7. This is on matrix vector equations. I'm your host, Tom Roby. So there's one main objective of this video lecture, which is to learn how to interpret a system of linear equations as being expressed as a single matrix vector equation. And we can also interpret that as saying that one vector lies in the span of several others. In other words, it can be written as a linear combination of the others. These points of view might seem like you're adding a lot of baggage onto the notion of systems of linear equation unnecessarily, but in fact we'll see that this point of view becomes very fruitful later on as we try to understand linear algebra more deeply. Okay, so here's the definition. You may have already seen a definition of the product of two matrices or the product of a matrix times a vector, and what I'm about to tell you is equivalent to anything that you've been taught before, assuming it was correct, which is likely enough. So here, we're going to define the product of an m by n matrix A, whose columns we're going to think of as A1 through AN. So if it's an m by n matrix, that means it has m rows and n columns. And so that means that we can think of each of the columns as being a vector, right? And it's a vector of length m because the matrix A has m rows. So we've got n vectors of length m, and I'm just going to say, well, if I multiply that by a vector of length n, and this n have to match, then I get just the linear combination of these vectors whose coefficients are the entries of the vector x. Okay? So matrix multiplication, multiplying a matrix times x, is exactly taking a linear combination of the columns of the matrix. Okay? Very important point here. So let's look at an example really quickly. So here I have a matrix with 2 rows, so m equals 2, 3 columns, so n equals 3. And so if I'm going to take a linear combination of 3 columns, I need to have 3 numbers to do it with. So 0, negative 1, 3. So the number of columns here has to match the number of rows, the length of this vector. Okay, so now what do? I just take 0 times the first column. That's 0 times 3, 2. Negative 1 times the second column, and 3 times the third column. I add them up, and of course I'm just adding coordinate-wise, and I get the answer 7, 9. Okay, so that's how you do the multiplication of a matrix times a vector. You get exactly a linear combination. And of course, this matrix also corresponds to a system of equations, right? This is the coefficient matrix for this particular system of linear equations. And what I'm really saying in the equation I just wrote down is that if I want to solve this system of equations equal to 7, 9, which is the output here, my x1, x2, x3 should be 0, negative 1, 3. Sometimes we'll write it as a row vector just for space reasons. Usually we'll write it as a column vector. So by this, I mean exactly the same thing as that. All right, so there's 3 things that are equivalent here. So we're saying that the solution to this system of equations is really just saying that this vector is a solution to the equation A equals B, where A is the coefficient matrix, X is this column vector, and B is the output column vector. Okay, and that's the definition. So let's just try quickly to do another example. I wrote it small here so that it would fit, but I'll write it bigger here. So suppose I have just a simple 3 by 2 matrix now, 3, 4, 5, 6. And now I multiply it by, what do I have to multiply it by? It's going to have 2 columns here, so that means I have to have a vector of length 2. So suppose I do that times 2 minus 1. What would this equal? Well, it's exactly the column 1, 3, 6 times 2 plus negative 1 times 2, 4, 6. And let's see if I can do that without looking at my notes. Going across, I get 2 times 1 minus 2. I think that's 0. I get 2 times 3 is 6. Minus 1 times 4 is 2. And I get 2 times 6 is 12. Minus 1 times, let's see, oh, this is a 6 here, right? So 2 times 6 minus 1 times 6 should be 6. So if I did this right, then the computation says that the product of this matrix and this vector is this vector of length 3. So notice that in this example, I had a 3 by 2 matrix. I multiplied by a vector of length 2. I got a vector of length 3. In this other example, I took a 2 by 3 matrix and multiplied by a vector of length 3 and got a vector of length 2. And those things are not accidental. OK, so now let's consider this at the level of theory. We'll write down a theorem. So suppose that A is a matrix, m by n matrix with those columns, and B is any element of R to the m. Then the following, TFAE is jargon in mathematics we use for the following are equivalent usually. In this case, I mean the following are equal. Trying to fit everything on the slides and still leaving room to write means that I sometimes need to use some shorthands. But the things that are equal are the solutions in R to the n of the equation AX equals B. Okay? So these are the things that I take the m by n matrix, I multiply them by x, and I get a certain output. So usually I'm given A and B, and I'm trying to find x. I'm given A and x, and I want to find B. That's straightforward, but it's harder to go backwards. So, but this is also the same thing as finding all the solutions in x. Ways of writing the given vector B as a linear combination of the columns. And finally, this is the same as the solutions to the augmented matrix. Okay, so the question you might ask is, when is there a solution? Is there anything we can say about how that works? And we sort of know, right? I mean, if we're given any particular example, we can do row reduction and see what's going on. But I'll be more specific about that in the next video. But let's just take a quick look here. Right? Suppose we've got this matrix, 1, 2, 3, 2, 4, 6, 2, 5, 7, going down the columns. So this is an augmented matrix. So my B is this 0, negative 2, negative 2. And so I just compute the row reduced echelon form if I want to make my life easy for the things. And of course, software can do that. And so now, what does this mean for the solutions? Let's just do this one out carefully in detail. Well, so this top equation is saying that x1 plus 2x2 plus 0x3 is equal to 4. And then the next equation is saying that x3 is equal to negative 2. Okay? So any solution will have x3 equal to negative 2. And then there's a relationship between the value that x1 and x2 can have. Namely, my solution is going to have the form. So x1, x2, and x3 has to be equal to, well, so x2 is a free variable, right? There's no pivot in column 2. That's why it's a free variable. The other variables, the pivot columns, correspond to the variables that are given in terms of constants and free variables. So x3 equals minus 2 is completely fixed. So I know this will always be minus 2. x2 is what it's a free variable, so it can be whatever it wants to be. But then x1 has to be 4 minus 2x2. Okay? So that is the form of a vector. And it's convenient often to write this a little bit more in the following form, which is to say, well, really, this is 4, 0, minus 2 plus x2 times negative 2, 1, 0. So did that make sense? What did I do? I'm just using the ordinary rules of vector component-wise addition and whatever. But what this means now is that, for example, if I plug in x2 equals 0 into this, I get what? 4, 0, negative 2. So that's this case. And now if x2 is, say, equal to 1, then I would get, so what are some solutions? So 4, 0, minus 2 is one solution. But so is, what happens when I plug in x2 equals 1? Well, I'll get 4 minus 2 is 2. 0 minus 1 is negative 1. And negative 2 plus 0 is negative 2. So 2 minus 1, negative 2 is another solution sorry, let's see, 2, 1, negative 2, I think, because I'm adding 1 times that, right? So 2, 1, negative 2 is another solution, and I could get as many as I want, right, by varying x2. x2 could be, 17 or the square root of pi or any number I want, right? And also I'll get a continuous line full of solutions parameterized by x2. Now, if I don't like the fact that x2 is my parameter because it looks like a variable, I can just change it. And so sometimes people will write things like, the solution set is the set of all vectors of the form 4, 0, negative 2 plus k times negative 2, 1, 0, such that k is an element of the real numbers. So that would be one way to legitimately write the solution. But I guess my main point is that if you want to get the output 0, negative 2, negative 2, there are lots of different ways you can do it. And one way you could do it is by taking the linear combination of these columns that's 4, 0, negative 2. So 4 times the first one plus 0 times this minus 2 times that. Or you could take the linear combination that was 2 of the first, 1 of the second, and minus 2 of the third. And you can double check that at home if you want to make sure that things are working the way they're supposed to be. Okay? So this will set us up for the next video with which this is paired. But I think that's it for now, and I thank you for your kind attention.